Hi, welcome to the last week for this module. We are at module 28. So in this module we are going to learn a bit of Verilog again, and what we are going to learn is something called an always statement. This is a very important category of statements in Verilog, and I am also going to show you how to mix different styles. So far what we have seen is, we have seen how to instantiate basic primitives, how to use basic primitives to imply logic gates. We have seen how to use assign statements, and we have also had cases where we actually instantiated sub-blocks and made bigger blocks out of it. For instance, when we did multiplexer, we designed 4-to-1 multiplexer using 2-to-1 multiplexer. So this is the fourth style of statement called the always statement. So I am going to talk about always statement for a while, and I am going to talk about how to mix different styles in Verilog. So let me switch to the design. So this is a design that you are probably familiar with. So I have a module called mux21. There is an output and a single bit output, and there are three inputs, select A and B, and we have already done this. Assign out equals not of select and A or select and B. This is something that we have already done. So if you think about this, right, what happens is, any change in the right side of A, right side here on A, B or select will in some sense trigger this statement to get executed, and the value that you get from this evaluation is assigned to the out signal. So if you look at the picture here, what we are having is, we have A, we have B, and we have the select line, and we have output. So this is our mux21, and what we want from any combinational circuit is that any change in any of the inputs should potentially change the output. Remember, combinational circuits don't have memory, right? So the current input must be able to drive the current value of the output, which means any change in any of these things should change the output. For example, let us say select was 0 and A was initially 0 and B, let us say, was a 1, and if A went from 0 to 1, we would expect the output to go from 0 to 1, because select is 0 and A is going from 0 to 1 without changing anything. Then the output should still get excited and move from 0 to 1. Or let us say A and B were 0 and 1, and select goes from 0 to 1, in which case you want B to be selected, again the output should go from 0 to 1. So there is no memory here. These inputs are staying as they are, and one of the inputs is changing, or one or more inputs can change. You would want the output to react to that, and that is the definition of a combinational circuit, right? So combinational circuit is essentially any change in input should reflect as a change in the output, and that is what we have in the assign statement here. So assign out equals not select and A or select and B does exactly that. So there is another alternative way to do that using the always statement, and this always statement is a lot more useful when you design sequential logic, but let me talk about combinational logic, and I am going to do the same circuit. I am going to design the mux21 instead using a always statement. So always statement starts with the keyword called always. So we'll look at this word always in a little while, and what we have is, I'm going to write down the syntax. We'll come back and look at what each of these things are. What do we want the always statement to get? What do we want the design to do? If there is any change in A, B or select, then the combinational circuit in some sense should have a re-evaluation of the output, right? So what I'm going to do is, all these three signals, namely select or A or B, if there is any change in any of them, then we want the output to react to it. So I'm going to put them in a list called the sensitivity list. So we have a sensitivity list here, and the sensitivity list consists of three inputs here, SEL, A, B. These are the three inputs, and if there is any change in any of the inputs, then we want the output to react to that. That is the meaning of this always at. So this at is if you press shift and you press 2, that is the symbol here. So in most keyboards you will see it as shift and 2. So always at SEL or A or B, and as usual I always put the begin and end before I do anything else. So now what we have is, we have a list, and I know that this always block, so we will call this the always block, is taking 3 inputs, select A or B, and it is supposed to process the inputs. So now I am going to introduce you to a new statement called the if statement. This if statement is very similar to what you have in C or C++ or any other language. So I will write it down and you will see that it is quite easy to understand. If select equals 0, then we want out to be equal to A, else out to be equal to B. So let us see what the statement is. So now I have the complete module, if you believe me or not. This is the complete module. I have the module description done. So always at select or A or B, there is a begin and end, and I have written something inside that. There is a if and then a else. So let us see what this is, what the meaning of each of these things are. So the first line that you see has a keyword always at what is called a sensitivity list, and it ends with a end. So there is a begin and end, and there is a if statement inside. This if statement itself has it's like any other programming language. If some condition, then some statement, else some other statement. Right? So now let us see how this whole thing is supposed to work. So as a module, this mux21 has input select A and B, and it has an output called out, and if there is any change in select or A or B, then this statement is executed. If there is any change, if there is no change, then this statement is not executed. So simulator is a piece of software, right? When we simulate this, if there is any change in select or A or B, then this statement gets executed, and the value that you get out of this is assigned to out. So let us try and save it and compile it now. So I will save this and I will run it. So I will run it once more just in case. Okay. So if you look at this, when select A comma B equals 0 0 0, out is 0, when select A comma B equals 0 0 1, out is 0, and so on. So this essentially at the end we also have this test case check. So this is the same test bench that I used earlier. So this is the same test bench that I demoed in the class earlier. I think it was in week 4 module 21, I believe. I'm not sure about the module number, but this is the same test bench then. So what we have is we replace the assign statement with something called a always block, and this always block is very fundamental to Verilog. If you want to model sequential circuits, you can actually do it only with always block. You cannot use assign statements to deal with sequential logic. You need always block for that. So I am introducing you to always block in this module, and I am going to do the same thing in a slightly different way, again using always block. Always at select or A or B, I will again put begin and end. There is also a case statement inside in Verilog. So case select when 0 out equals A, let me try and make this small, out equals A, when 1 out equals B, and Verilog there is a clause for default, and by default I am going to assign A. I am going to assume that by default the input is 0 itself. I will assign that, and case has something called an end case. So my claim is that the always block that you see here and the always block that you see here are actually equivalent to each other. So both of them take select A and B these three inputs in the sensitivity list, and this statement, the case statement here, is equivalent to this if then else statement here. So let me comment out this part and show you that this part actually works and it's correct. Let's check that. So I've saved it and I'm going to run it now. Let's run it. And again, as before, all the test cases passed, and this always block seems to be correct. So this always block that I wrote here seems to be correct. So one thing that you have to notice is the sensitivity list has SEL OR A, OR B. So this OR is not the same as bitwise OR, and this is not even the same as logical OR that you will use in conditions. So this OR is used in the sensitivity list. You can think of it as a list of signals, a list of inputs that this always block will get excited upon. That's all. So do not attach any more meaning to this OR here. It's not doing logical evaluation of select A, B with a logical OR. It's not doing that. So keep that in mind. It's just you can think of it as a separator between these three inputs, select A and B. So if there is a change in select, or if there is a change in A, or if there is a change in B, execute the statement. Whatever comes out should be given to out. So when you execute the statement, out either gets A or B. And there is a default clause. This default clause is actually a safety net, and I will talk about the safety net in more detail when we handle sequential circuits. So it's always a good practice in a case statement. If you are going to talk about some combinational logic, it's always a good idea to have a default clause, and in the default clause I have put out equals A. So now I want to show you a little bit of an interesting thing. So I talked about the sensitivity list, right? So going back to combinational circuits, any change in select A or B should make the circuit reevaluate and possibly change the output, right? So now I am going to show something really nasty that can happen if you forget things in the sensitivity list. So I am going to remove this B from the sensitivity list. So the sensitivity list has only select or A, right? So otherwise the code inside looks exactly the same. I didn't change the code inside. So it earlier passed, but I have only changed the sensitivity list now. So let me see what happens now. I am going to save this and let me run it again. So something happened. So I will show you what has happened. Let me pull this up. So things seemed like they are working fine. When select A comma B is 0 0 0, out is 0. When select A comma B is 0 0 1, out is 0, and so on. So you can check up to this line here that the output is actually fine. So let's see let's look at all of these. Select is 0 for the first 4 lines. So when the select is 0 for the first 4 lines, output is supposed to follow A. So it's following 0 0 1 1. So far it looks okay. Let's look at the 5th line. When select comma A comma B is 1 0 0, out is 0. So this looks like it's actually correct, right? So when A comma B, so select is 1, you are supposed to choose B, and it looks like it's actually taking B and it's putting 0 there. Let's look at the next line. When select comma A comma B is 1 0 1, out is 0 is wrong. It's wrong because when select is 1, output is supposed to be B, which is actually 1. However, it shows 0. So there is something wrong here. The reason that it is wrong is because in the sensitivity list we have actually removed B for this statement. So in a combinational block, any change in any of the inputs is supposed to affect a change in the output. So let's see this line. In this line, when the simulator evaluated it, select was changing, right? Select was changing from 0 to 1, A was changing from 1 to 0, right? These two are enough to trigger the case evaluation of the case statement. So it evaluated it triggered the evaluation of the case statement, and in this case out equals B, so out is 0, which was okay. if you go and look at this line here where it was correct, where it was last correct, and if you look at the line here where it actually went wrong, the only thing that has changed is B. So select is remaining the same, A is remaining the same, B changed from 0 to 1. When B changed from 0 to 1, as a combinational circuit, this mux21 is supposed to have reacted to that. But since B was not in the sensitivity list, it didn't evaluate this case statement once more, and the output was the previous output itself, which was 0, and this output equal to 0 is actually not expected in the test bench. The test bench is actually expecting a 1. So the test bench is reporting that this case is incorrect. So you have to be careful. You have to put all the signals for a combinational block. Right? If you are implying a combinational circuit, you should have all the inputs in the sensitivity list. So I will go back and save it and run it once more and ensure that it's actually okay. So all the test cases are passing. So this is the basics of an always block. So an always block can have statements which are actually called sequential statements inside, and we will talk about the notion of concurrency and sequential statements in a later class. But as of now, you know how to write an if then else statement, and you know how to write a case statement. So let's look at the next case. So I said the other thing that I will talk about is mixing different styles. So what I have done is I have written a mux21, which was the original thing, which had an assign statement, and I have mux21 version 1. So I have another module called mux21 version 1, which seems to have if then else kind of writing, and there is mux21 version 2, which has case statement kind of writing. So there are 3 mux21s here. The first mux21 is an assign statement, is using an assign statement. The second mux21 is using the if then else, and the third one is using the case statement. So one thing you have to remember is these statements inside do not have the keyword assign. So when you look at always block will not have an assign keyword inside. So this equality here, this equal symbol here versus this assignment here, they are actually different things. We will get into the semantics in a later class, but you cannot put a keyword assign here inside the always block. So now what we have is we have 3 different ways of designing the multiplexer. We have a multiplexer which is designed using a logical equation. We have another multiplexer design, so it's the same mux21 but designed using if then else statement, and again another multiplexer designed using a case statement. And there is a mux41 here. This is something that I again showed in an earlier module, and this mux41 is a 4 to 1 mux. It seems to have 3 different muxes, M1, M2 and M3, and they are all now of the type mux21. So if you go back, mux21 is use the assign statement. Now let's first run it and check whether it works. So I wrote the test bench for it. So I didn't show it to you in the last class, but I have a test bench which I can put online. You can check it later. So this test bench is not checking for whether things are correct or not. It's just printing the output, and believe me, it's correct. So what I want to show is that these 3 multiplexers, right? The first thing I want to show is that it looks like there is some order in which we have declared all these declarations. We have done all the declarations. So this mux21 M1, mux21 M2 and mux21 M3, it looks like we designed the M1 mux first and then instantiate the M2 mux, and then we have instantiated the M3 mux. So if you come from a sequential programming language like C or C++, you have to assign values before you use them. So it may look like temp1 and temp2 has to be assigned values before giving it to mux21 M3. What I am going to do now is I am going to take that, I am going to put it on the top. Okay. So I want to show that first of all the order of statements inside a module doesn't matter in Verilog. So I have moved it up and I am going to run it once more. Right. That did not really change anything. Again, you can verify this locally yourself. There will be several lines here. There are 64 lines in which various inputs and outputs are shown. The first thing is it didn't complain about this temp1 and temp2 being different. right? This temp1 and temp2 are supposed to be driving M3, but I put declaration of M3 before the declaration of M1 and M2. That's actually perfectly fine. So what we have is all these three statements are actually instantiating gates, and what we have done is we have said we want these three gates and we want the connection between these gates. The order in which we have to actually put them is not specified, and that's perfectly fine. So that is the first one that I wanted to talk about. The second thing I want to talk about is you can actually mix and match styles. So what I am going to do is I am going to use version 2 for M3 and I am going to use version 1 for M2 and the assign statement version for M1. So what I have done is I have actually instantiated three different multiplexers of different kinds. So M3 is going to use version 2, which has this case statement. M2 is using version 1, which has the if then else version, and M1 is using the assign statement. So Verilog allows you to mix and match different things, and what we have is we have what is called different architectures for the same design. So if you know VHDL, the MUX21 is an entity, and what we have is three different architectures. So Verilog does not give you the same facility like entity and architecture like VHDL does. We have three different versions: MUX21, MUX21 VER1 and MUX21 VER2. We have three different versions, and in a single design MUX41 we have instantiated three different kinds. That's perfectly okay. So this is another mechanism. You can mix and match styles that are appropriate for the design that you are looking at. So I want to show that this is possible. So it's a very silly example here, it's a very simple example. However, I want you to know that such a facility is available in Verilog. Verilog does not restrict you to only one form or the other. All the forms that we have seen so far, namely using primitives, using always blocks and so on, can all be mixed. In fact, I don't have to instantiate a mux here. I can write an always block to do only one of these, that would also still work. So probably this is a little too much to digest right now. As of now, just trust me that there are three different instantiations here, and these three instantiations have actually used three different styles. That is perfectly okay. Even within a single module, you can actually have different kinds of blocks mixed together. You can have an assign statement, you can have some primitives, and you can have an always block, and that's perfectly fine. Verilog will actually allow you to do that. So in this module, what we have done is we have seen two things. One is we have seen something called the always block, and the always block is something that actually goes inside the module, and you can actually have what are called sequential statements inside. I'll talk about what this notion of sequential is. This is not the same as sequential design. So there is something to do with the order of execution of statements inside a always block, and we also saw how we can actually write different things and mix them together in when I talked about multiplexer 4.1. So what we have done in from week 1 to week 5 in terms of Verilog is that we have seen how to write basic modules all the way up to the 4 fundamental ways in which you can write design. You can instantiate, you can use primitives, you can use always block, and you can use assign statement. In fact, when you instantiate, the underlying model should use one of the three, should use either primitives or should use always blocks or should use assign statements. So the instantiation is just a meta thing, but the underlying things are you can use assign statements, you can use always blocks, or you can use primitives directly. So what we are going to do is we are going to see larger and larger designs done with these styles, different kinds of styles, and from next week onwards what I will talk about is how to pick an appropriate style for the design that you have at hand. If you have multiple choices like these, how do you pick the right way to do things? When should I use if statements versus a case statement? When should I use equations like in an assign statement versus an always block? This is something that usually comes with practice, but what I want to do in this course is give it to you straight so that you start in the correct way instead of experimenting with various things. Like with any programming language, there are hundreds of ways in which you can do things, but designers who work and make large designs do not fool around with Verilog and try to play with different ways of doing things. Usually I as a designer, what I do is I pick one way and I learn it well and I use it over and over instead of figuring out all the 100 ways in which things can be written. So this brings me to the end of week 5 also, by the way, and in week 5 we saw a lot of heavy duty stuff. We saw basics of electrical circuits, what are the fundamental electrical parameters. More importantly, I introduced you to the notion of delays as well as state machines. So this week is quite loaded, and on top of that I have also introduced some new topics in Verilog. I suggest that you spend a lot of time this week in reviewing the material, because the quiz is also going one level up. The kind of questions that are there in the quiz is also going to go one level up. So till now we have had quiz questions which are fairly simple and straightforward. From this week onwards you will see that the quiz is also drifting its level up. I recommend that you actually go back and review the videos, use the forum very strongly, ask questions on the forum. I'll be there on the forum along with my TAs, and there will be others in the classroom also. So I suggest that you take a serious look at the forums before you before you ask your own question. Right? Find out whatever other people are asking, what I am replying and what the TAs are replying before you shoot off your own thread. So I am hoping that you have been enjoying the course so far, and I did look at the feedback that you have given, and I am waiting for many others to give the feedback. I will talk about the feedback itself in a later class, and I am also already beginning to fix many of the things that you have mentioned in the feedback so far. If you have not given feedback, I suggest that you go back to the Google spreadsheet link that I gave you and give your feedback, because it is very valuable for us. So thank you very much, and see you next week. Bye bye.